So Unit 2 has two parts to it. The first 2 weeks are business statistics. Business statistics, we're just doing a very, very quick overview of statistics in this course for 2 weeks. I could probably do somewhere around 32 weeks if I wanted to on statistics. It is probably the most useful math topic you will run into as far as decision making and stuff like that. What we're going to cover in the next 2 weeks is just touching on it. So we're going to hopefully get more towards the understanding of it rather than being able to actually do a whole lot with it, because 2 weeks is very quick to get through it. But many of you, if any of you decide to go on to a bachelor's degree, I'd say 80% shot that you're going to be required to take the statistics course at some time. Statistics is where the decisions get made. If you look at major corporations, your CEOs and your vice presidents, I saw a statistic once on corporate vice presidents, and it was like 92 or 93% of them had backgrounds in either statistics or accounting. So you need to need to know how to understand the numbers or know how to understand the money, one of the two, to get up to those levels. And then the last 2 weeks, weeks 3 and 4, are going to be on merchandising. Merchandising is your invoicing, your pricing, stuff like that, getting goods from the manufacturer to the consumer. So let's have some fun with statistics here. Well, to start out with statistics, we're going to have to start out with a ton of vocabulary. I'm going to limit it to the very minimum of what we need here for now. Statistics really is almost like a foreign language because there's so much terminology in it. So we're going to keep down to the bare minimum. But the heart of statistics is analyzing numbers to make a decision. There are two types of statistics. There are descriptive statistics. Descriptive statistics are just for that. They're to describe or summarize what's going on. And then there's something called inferential statistics. Inferential statistics are used to make a decision or some sort of a conclusion. They're not independent. We usually draw upon the descriptive statistics in order to do the inferential processes that we do. But obviously the inferential statistics are a step above. For what we're going to be seeing in here over the next 2 weeks, it's going to be pretty much all descriptive statistics. I might hint in a couple of spots of how you could use this to make a decision, but it's really not inferential statistics. Descriptive statistics are necessary to give you the information to make informed decisions, but we're not going to actually get into those statistical decision-making processes. Partly because we're not going to have time to get into probability, and what links the two of these together is probability. You gather the descriptive statistics, then you check the probabilities, and you use that to make the decision. And probability is about a 3-week topic on itself, so obviously we're not going to be able to get into that here. So more vocabulary within our statistics. Probably the most important word in the field of statistics is a population. A population is the group, whether it's people, products, items, whatever, it is the group that we want to learn about. Now this it's the most important thing we can do is to define the population, but it's often not as easy as it sounds. For example, just had a presidential election not quite a year ago. If I want to learn, I want to predict the winner of the next election. What is my population there? What group is it that I want to learn about? And that's where most people go. The president, the candidates, the winner, you know, that's it. The candidates themselves don't determine who wins. It's the people that are going to cast the votes. So we get here, bless you. We want to learn about the voters, but not, a lot of people say, well, we want to learn about all registered voters. Not really. Which voters do we care about? The ones, bless you again, the ones that are actually going to vote. If they're going to sit at home on election night, we don't care about them. We only care about the ones who are actually going to vote. Now, do we know which ones are going to vote? No, because for some of the smaller local elections, if you're like me, I may not know if I'm going to vote until the day it happens. It depends on if I get time off work or whatever. So there's some problems there. Because of that, we tend to choose a sample. A sample is nothing more than the technical word is a subset. Subset just means a smaller group chosen from the population. And there are several reasons why we would choose a sample. One is the one that I just gave. Unclear population. Yes. Okay. So that unclear population, like I said, it's hard to define the population because it's really not totally sure what's in it, and some of the members of the population aren't sure whether they're in it or not. Now, the obvious reasons for choosing a sample. Now my computer's going to act up. The most obvious reason, money. If it's a local school board election or something like that, it may not be quite so difficult to survey a large share or all of the possible voters. If it's a presidential election, a national election, it would be really tough. It would be very expensive. And of course, along with money is time. By the time you got in touch with all those voters, that'd be a lot of time. And of course, time and money are very tightly related in that sense. Some ones that are a little less obvious. Now, this is not time. What I'm going to talk about here is not time in the sense of it takes more time than what you're willing to give to it. It's changes over time. This is where the example of the election fits in well, because conditions change over time. Let's say I start surveying, I start calling potential voters to see who they're going to vote for on Monday. And Monday and Tuesday, I call them and I gather this information. Well, Tuesday night, one of the candidates goes on television and says something really stupid. It's a big surprise, huh? Wednesday, I keep calling potential voters. Am I still doing the same survey? No, the conditions the conditions have changed. After that comment was made, many of the people I surveyed before may have changed what they're going to vote for. So it's not the same survey anymore because it's not done under the same conditions. So changes over time or changing conditions. All the information has to be gathered under the same conditions, same atmosphere and everything. Once that candidate comes out and says that stupid thing, my survey has to stop. The data from before and after are separate. They can't be compiled together because they're not related anymore. This fifth one does not necessarily relate to surveys or political surveys or anything like that. It relates to manufacturing and data gathering there and testing. At least I hope it doesn't relate to surveys. It's destructive testing. What I'm talking about there is, let's say you're working in a quality control position in a manufacturing facility. They produce these parts, and those parts have to be able to hold a certain amount of force. They have to meet a certain standard. So they take those parts, they pull off the assembly line, let's say that's the part, they put them in a machine that's going to stretch it. And normally what they do is they stretch it until it breaks, and they read on the machine tells them how much force it took to break. Can they test every part? Well, they could, but testing it breaks it. If they test every part, there's nothing left to sell. So they have to choose a sample. They have to test enough of them that they can be relatively sure that the others are probably good too. And there are other smaller, less prominent reasons to take samples over testing the whole population, but you guys get the picture. Here's a statistic then is a piece of information describing a sample. So let's say we took a sample of, I'll say sample size. The letter we use to represent sample size is the small letter n. So you took a sample size of 300 voters. That's a statistic that describes our sample. %62 of the sample support option A, whether that's a candidate or a proposed law or whatever. That's a statistic. It describes our sample. A parameter is similar to a sample, but it's a piece of information that doesn't describe the sample, it describes a population. Most often, parameters are estimated. If we knew the exact parameter, that means we had access to information from the whole population. If we did that, there's no reason to take a sample and do a survey. So usually we do the survey, we take the sample and use that to estimate the population. So we might say, based on our survey, we would conclude that more than half of the population supports option A. It's an estimate, it's not an exact number, but it is describing the population. That is a parameter. When we do these studies, there is a variable involved. Now, I'm not talking about a variable like x equals 7 or anything like that. The variable is, what do we want to learn? More specifically, these studies, whether it's a survey that we're doing or whether we're testing that part, we are asking a question. The question might be, do you support this proposal? Or who are you going to vote for? Or how much force can this part hold before it breaks? There's questions. The variable is the answer to that question. The official name is a random variable. If this were a longer statistics course, we would talk a lot about random variables. We're going to come back and talk a little bit about them before we're done, but we're going to put that on hold for a little while. That question, though, that we're asking, that random, that variable, that piece of information we're trying to gather, we're trying to avoid something called sampling error. What that is the difference between the real amount and the sample amount. So let's say our sample came up with 62% supported option A. In reality, 57% of the whole population actually support it. Our sample was off by that amount. I don't want to say 5% because that's kind of a confusing way of stating it. But our sample was not exactly the same as what our whole population would be. That's sampling error. How do we minimize sampling error? Which is the goal of a lot of the things we do in statistics. Well, we take something called representative sample. A representative sample is where the sample amount and the real amount are exactly equal. The problem is we don't know the real amount, do we? So we'll never know if they're exactly equal. So we want to take measures to try to minimize that difference. The way that works, a representative sample requires two things. One, adequate size. I cannot call two people, ask them who they're going to vote for. One of them says, I'm voting for candidate A. The other one says, I'm voting for candidate B, and turn around and say 50% of the people support A. That is too small of a sample. Second is randomly chosen or properly chosen. To define properly chosen, I need to define that word random. A random sample is a sample in which every member of the population has an equal chance of being chosen, of being in the sample. It is not as easy as it sounds to get a random sample. Political surveys, by the way, that you see on TV are never random samples. The reason being why is how do they gather the information for most of those political surveys? How many of you have been sitting around the supper table, and not so much anymore, but what's that? Phone calls. Sitting around the supper table, you get that phone call. Would you like to take a survey? Yeah. Oh, no, I have fun with them. Anyway, who is that left out? Do you think there are people that are going to vote for president that don't have a telephone? Yes. So that if that's how they're gathering information, that's already by definition not a random sample. In practice, it's not as easy to take random samples as it sounds. So we get them as random as possible. Now, there's a lot of methods of sampling. We're not going to go through them here because this is not an official statistics course. There's systematic, there's cluster samples, there's simple random samples, there's all sorts of them out there that you would hear about. But I'm trying to limit the vocabulary. So anyway, let's get back to that variable that we talked about. That variable is the answer to the question we're asking. Who are you going to vote for? Do you support this proposal? How much force can this part hold? How tall are you? How much money do you earn? How many credits do you have? Whatever those questions are, the answer is the variable. So there are two types of variables. There are numerical variables. Sometimes, depending on what textbook you're looking at, called quantitative. For this class, I'm going to refer to them as numerical because numerical means that answer is a number. Examples of numerical or quantitative variable. Height, how tall are you? Time, how long does it take to do this? Age, how old are you? How many questions? How many cars do you own? How many credits are you taking? How many classes are you in? How many children do you have? Too many. If you had your way, one less. How many questions? This is what numerical variables are. There are two types of numerical variables. It's continuous and there is discrete. Now, I've heard a lot of definitions of these two types of variables before. The best definition I've heard, the easiest one to remember I've seen is this one. Discrete are things that are counted. How many kids do you have? How many credits are you taking? How many cars do you own? Those are things you can count. Continuous are things that are measured. How tall are you? How much do you weigh? How long does it take to do this? Those are measurements. Now, there are some things that kind of blur the lines in between. Like, how much money is in your pocket? Well, do you have to measure your money? No, you can count it. Money goes down to a penny. So that becomes discrete. Although, if you want to get into more technical, more mathematical definitions of continuous and discrete, discrete means that there are gaps in between numbers. Like you go from 1 to 2 to 3, but you can't have 2.5 or 3.5. Or you go from 1.1 to 1.2 to 1.3, but you can't have 1.15. Things like those are discrete. There's gaps in between. Continuous is there's no gaps in between. A technical definition of continuous is no matter how close two numbers are together, you can find a number between them. So those are continuous variables. I like just measured and counted, though. Those are pretty simple. So those are types of those numerical variables. Then, of course, we have categorical variables, sometimes called qualitative Qualitative variables measure a quality of the person, not a quantity of the item, not a quantity of the item. Categorical puts you into a category. Examples of categorical variables. Come on. Favorite color. It puts you in a category of people who like red or blue or green or purple. Any yes or no questions, because it puts you in a category. You're either a yes or you're a no. You're on for or against. Town that you live in. Your major, your degree program. Those are all categorical variables. The answer is a category. It puts you into a category. So then we're going to talk about organizing data. And before that, I should probably talk just a little bit about what data is. Data is data or data, depending on how you pronounce it, is that list of answers, all of those answers to that question you're asking, all of the different results. I mean, I could do a question of what are your scores on this test? The data would be each individual test score. Those are the pieces of data. So now we're going to look at organizing that data. And of course, there's two different types of data to organize. We're going to talk first about organizing because it's quicker. Categorical data. Let's say that we ask a question of favorite color. And we give people a choice of red, blue, or green. Those are your only choices and you have to pick between them. Now, I'm not going to go around the room and ask you your favorite color for the sake of time because I'm getting long-winded. So I'm just going to make up some data here. So let's say I ask people, I get a red, a blue, a red, a green, a blue, a green, a blue, 7, 8, 9, a green, a red, a green, and a red, a green, a red, green, green, blue, 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 green, blue, green. That was an enthralling portion of the lecture. Huh? So we have those 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 24 responses there. N equals 24. That's the size of our sample here. When it comes to categorical data, there's really only one first level of organization. The first level of organization, of course, from the raw data, this is what we call the raw data or raw data. The first level of organization is to put it into a table. And about the only table that's really statistically valid, it's called the frequency table. So in the frequency table, we list what it is that our category is. In this case, it's color. Then we're going to list the frequency. Now, this may sound like a silly question, but I'm going to make a big deal about it here, and I'll explain why after a while. We have three colors, three categories, red, blue, and green. Doesn't matter what order I put them in. No, it would make sense no matter what order I put them in. So I'm just going to go red, blue, and green. I'm going to go up here and I'm going to count how many red I have. First of all, looking at this table, can anybody tell me which one occurs more often without counting? Okay. It all depends on where you look. This is one of the reasons why we organize data and summarize it. because the human brain, psychology tells us the human brain can really only take in between 7 and 13 things at a time. So you cannot, there's 24 up here, you cannot look at this and see the whole thing at once. If we're looking over here, I would say that looks like red. Looking over here, I'd say probably blue. Down here, most likely green. Now, it depends on how good of a job I did here. But let's count and see. 1, 2, 3, 4, 5, 6, 7 reds. Blues, 1, 2, 3, 4, 5, 6, 7, 8 blue. And 1, 2, 3, 4, 5, 6, 7, 8, 9 green. You're correct. Looking at that list, would anybody have guessed green was the most common? Not really. You know, blue and red both. You know, somebody did. Okay. Blue and red usually, because of the way I grouped them, look like they're the most common. But green was the most common there. That's why we need to organize the data. Looking at that raw data, it's so easy to get yourself wound up and confused. Almost impossible to get an impression of what's the most common. So that is a frequency table. From a frequency table, we can create something called a relative frequency table. Relative frequency and percent frequency, depending on what textbook you're looking at. Some textbooks consider them to be the same thing. Some consider them to be slightly different. To me, they all say the same thing. To find the relative frequency, we first must find the total. Well, the total here is 24. Then the relative frequency is just each frequency divided by the total. 7 divided by 24 is 0.2933, something like that. 1.6. Okay, I missed it. 1.6, yeah, 7, something like that. So that would be the relative frequency for red. For blue, it's 8 divided by 24, 0.33333. For green, it's 9 divided by 24, which is 0.375. So, first of all, these should add up to about 1. They might be 0.999 or 1.001, whatever, but they should be about 1. It tells us what portion of the time each of those occurs. Now, percent frequency, using what we learned about percents, we're just moving the decimal point. 29.16, 33.33, 37.5. We've got it all figured out, right? Of course, the percents should add up to close to 100%, either 99.99 or 100.01 or whatever. So that's organizing categorical data in a table. The next step from a table, well, let's talk about the strengths of a table. First of all, strengths of a table is that it shows exact frequencies, exact numbers. I can look at the table and get exactly how many blues or how many greens there are. The weaknesses, well, here I only had 3 different colors, but what if I had 12 different colors to choose from? It might take a while. Yeah, it's slow. If I ask you which one is the most common, you've got to look through 12 numbers and figure out which one's the largest one. It might be a little slow. So to fix this weakness, we use graphs. Graphs are just the opposite. Their strength is they're fast. You can very quickly look at a graph and pick out the largest number or comparing to. Their weakness is it's hard to get exact numbers. One type of graph I could do with categorical data is called a bar graph. A bar graph can be either vertical or horizontal. Horizontal bar graph. Bars run horizontally, so that means my categories are on the side. Doesn't matter what order I put those colors over there. Is there any logical order that I should put them in, or two that belong next to each other? Not really, is there? On the other side, then, in this case, the bottom, I have to put a numbered axis. Now, these numbers are relatively small, so I can label them individually. Green was 9. So right about here. So I make that bar of 9. Blue was 8. So I make that bar go to 8. And red was 7. So I make that bar go to 7. Notice the bars, there's separation between the bars because there's no real connection between the labels. Or I could do a vertical. In a vertical bar graph, the categories go along the bottom. Again, notice I changed the order. Doesn't matter, does it? We don't have to label the axis by ones. I can label it by 5s or 10s or whatever. Here, I probably should have labeled it by ones, but I'm making a point. Green is 9. Red is 7. Blue is 8. So again, you can very quickly look at that and pick out which one's the most popular, which one's the least popular. Or if I asked you to compare blue or green, which one is the most popular, it's easy to see that the green is taller than the blue and so on. You'll notice I maybe wasn't quite as careful on the vertical one, but I was careful on these to make the bars the same width. That's one thing that is very commonly done. What matters there is just the height, right? But looking at it, your mind is drawn a little bit to that red, isn't it? Because it's wider. Now, in this case, you probably still realize the green is most common, but it would be much more effective if I did this. Here's red. Here's blue. There's green. You can laugh, but that is used way more often than you would think. Of companies doing advertising or doing a pitch to an investor or whatever, you look at this, all that matters, let's say these aren't colors, they're companies. You know, this is the production of our company, this is the production of our two main competitors. All that matters is that height. We're just a step away in each case. But boy, that looks impressively large. Here's the other thing that gets done. Come on now. Here we go. Let's say we want to compare annual sales. companies A, B, and C. Looking at that, how would you compare the sales for company B to the others? It looks like it's almost twice as much, doesn't it? If you look closely, though, what do you see? This is 2000, that's 2010. This is probably about 2003. This is probably just under, we'll call it 2010. This one looks about 2002. Is there a huge difference? Why does it look like such a big difference? Yeah, this little symbol right here means we broke that line, we broke the scale there. We didn't start at 0, we started at 2000. If we had started at 0, there's 1000. There's 2000. Oops, I did that backwards. That C is supposed to be a little shorter, isn't it? Can you even hardly tell the difference between them? No. I mean, there's advantages to this. It allows you to see if those data values are really close. It allows you to see the difference. But also, if I'm company B, I'm using that graph because it can be misleading. If you get nothing else out of this course about statistics, I mean, you're going to have to do some of these calculations on a test. So hopefully you get a little bit more than this. But a year from now, if you remember nothing else about the statistics in your course, this is one of the biggest things I want you to remember. Statistics can be very misleading. The final type of graph that I want to show you for categorical data is a pie graph. And a pie graph uses the percent frequency. That was the raw frequency, or just the frequency. In the pie graph, we're going to use the percent frequency. Now, if this were a course, 20 years ago, we would calculate, we'd have that percent, and then we'd take 360 degrees. We'd calculate that percent as, what percent is that, how many degrees is that percent out of 360, and then use a protractor to measure it out. Well, we have technology that does that for us now. If we wanted that perfect of a pie graph, we'd go in Excel or something else, and we'd make that perfect pie graph. So now all we really need to know for this course is this. 1/4 of a circle is 25%. Half of a circle is 50%. And then any variation in there. So looking at our numbers, we had 29.16. A little bit more than a quarter, right? That was red. We had, what, 33%? That's going to be a little bit bigger than that. Looks like that. That'll be our blue. The rest is green. Notice green is still bigger than the others. That's close enough for our purposes. We don't have to be exact with it. Okay, I'm 2 minutes late on our break, so let's take our break here. Okay, so we've looked at organizing categorical data with a frequency table and with graphs. So next we're going to look at organizing numerical data. And for numerical data, we are going to have to separate it out into our discrete and our continuous. So we're going to look at discrete first. Discrete actually can be the more complicated of the two. We're going to start out with the simplest case first, where we have not only discrete data, but we have a limited number, a very small number of values. For example, we might do a survey of students of number of classes enrolled in right now. And let's say if you have 0 classes, you're not a student, so 0 isn't a possibility. Let's say nobody that we surveyed had more than 5 classes. So because there's only 5 different possibilities, we can list them all out. And let's say we did our frequency, and in our survey we found that there were 8 students that had 1 class, 13 with 2 classes, 19 that had 3 classes. Oh, what do we say that there? 40? 7 with 4 classes and only 3 with 5 classes. So there's our frequency table for discrete data where it's a limited number of possibilities. If we change that question, though, rather than saying number of classes, and we asked for how many credits you're taking, well, we have students taking up to 19 or 20 credits. So going from 1 to 19, that's a lot of different numbers to list out. Probably more than we want to. So we might group them together. We might go 1 to 3. Now that means the next one's going to start at 4, and it's going to have to go up to 6. This went up by 3. This one's going to have to go up by 3 on the end, right? So it has to, making sure those groups are the same size. So the next one would be 7 to 9, exactly. And then 10 to 12, 13 to 15, 16 to 18. Let's say 18 is as high as it went. Mainly because I'm at the bottom of my paper and I don't want to list anymore. But now, this is one of the problems with doing groups like this. These groups are called categories or classes. When we do those classes, we break it up into groups like that. The hardest part is figuring out what size to make the groups. Here, what if there was a student that had 19 credits? Well, we'd either have to add another group or we'd have to go back and redo them. Might have to be 1 to 4 and 5 to 8 and so on. So that we make it. The biggest question is how many classes to have. And that sounds like a simple question, but it isn't. One of the things about statistics that's frustrating for people in math that are used to math saying this is the right answer, in statistics, there are a lot of gray areas. There are a lot of spots where it could be the right answer or it could not be. There are several different fields of thought in statistics. This is one of those areas where it is, determining how many classes are enough. Well, some say you take the number of items in your sample and you take the square root of it, and that's your number of classes. Or others say you divide the size of your sample by 10, and that's your number of classes. There's all sorts of weird formulas and weird suggestions out there for your number of classes. The key is I just fill it out, and here if I did need 19 and I decided 7 classes was too much, you try again. Now on a test or anything like that, when I ask you to make a class, I'll give you the first one like I did here. I'll give you that 1 to 3, and you just have to go from there. But it's okay. We've all been there. Don't worry about it. I see you over there covering up. Don't be embarrassed. If you need to grab the garbage can and the Kleenex, go ahead. Pull them over there by you if you have to. So you might even you get the classes, and the classes look just fine here, but you might go to fill in frequencies and realize, well, this is 11 people there, and 19 people here, and 3 there, and maybe only 6 here, 17 and whatever. You might get those numbers in there and realize, well, we got some classes that don't have many in them. If we rearrange them, we get bigger numbers. You don't want to have so many classes that you have really small numbers for your frequency. And you don't want to have too few classes that all of your numbers are really large. Generally, I know it's a lot of work, but the best way to tell if your classes are the right size is to go to the next step. Which is to start graphing these. If you make a histogram is basically a bar graph for numerical data, and it's always vertical. Now here, does it matter what order I put these in down here? It kind of does, because it goes from one to the other. Whereas with the categorical ones, I could put them in any order, and any order made sense. It wouldn't make sense to put the 10 to 12 in front of the 4 to 6. Now I'm going to put up the side here, we're going to have, some sort of scale again. I need to go above 20? No. And then we're going to put in our bars. We had 11 and 19. Is it 3 and 6? 17 and 4. Now looking at this, that graph has a nice, there's not a lot of empty, there are no empty spaces. First thing that would be an indication that my classes were bad is if there's spots on here where there is no bar, that it's empty. That would indicate you probably have too many classes. Have fewer classes and make them bigger. These bars have pretty good variation. They go up and down. So that tells me it's probably pretty good classes. If it looks something like this, can't tell a whole lot about the shape of the data there. I probably need more classes than that. That's all I'm going to say about getting those classes, because like I said, that is it's a difficult subject. Trial and error is really the only way to do it. On a test, I'll give you the first class, and you just have to go from there to fill it out. So, of course, you do make histograms is the most common one made off of those. You can make circle graphs, similar to a pie graph, off of those. Continuous data. For continuous numerical data, we have to make those ranges, those classes. Continuous data might be looking at height. So we might take a survey of people and get their height, and we might have 63.2 inches, 69.4 inches, 65.8, 71.3, 74.1, 64.7, 70.8, 66.3, 67.4, 72.5. I could make a huge list, and it's very possible to not have any two heights that are exactly the same. So the only way it's going to make any sense to group to put these in sort of a table or got my tongue tied. The only way it's going to make any sort of sense to put these in a table or a graph is to group them together, similar to what we did with this discrete data when we had too many possibilities to list them out. So here, now this is just a small set of data. The classes I'm going to make up aren't going to fit it real well. Well, let's say we have numbers that go from 60 to 75. So I might do 60 to 64.9, 65 to 79.9, 79.9. How about 69.9? And then 70 to 74.9. Let's say none of them actually quite reach 75. First of all those classes are the same size. It goes up by 5 here. It goes up by 5 there on all of them. Frequency. Now I'm going to show you guys a trick for frequency. I wouldn't include this in a finished table, but when I'm creating the table, if I'm doing my rough draft, I'll often put a tally column in there. What that means is I can go up here to my data, 63.2, that's between 60 and 64.9. 69.4, that's between 65 and 69.9. 65.8, that's in that one. 71.3 is in there. 74.1 is there. 64.7, 70.8, 66.3, 67.4, 72.5. Just put those tallies in there. Now I can see, okay, this is 2, 4, and 4 are my frequencies. Again, in my finished table, I would not have that tally column in there. I would take it out. But when I'm creating it, it helps to have it in there to make that rough draft. With continuous data, it's occasionally done with discrete data, but it's more common in continuous data. We sometimes create something called a cumulative frequency table. What a cumulative frequency table does is it uses these same classes, but it's going to rewrite it a little bit differently. It's going to write it like this. Instead of from 60 to 64.9, it's just going to write in less than 64.9. The frequency, of course, is just there's going to be 2. There's 2 that are less than, maybe put less than or equal to 64.9. The next one would be less than or equal to 69.9. Well, there's 4 in that category, but there's 2 that are smaller, so that's going to be 6. Then less than or equal to 74.9. There's 4 in that category, but there's 6 that are smaller, so now it's a total of 10. Notice what happens there is it builds up. It's adding up, starting at the smallest one, then adding on to it as we get up there. This bottom number here, digits keep disappearing on this thing tonight. That bottom number there, the 10, would be the same as the total frequency on my regular raw frequency graph. Does that make sense? I'm not going to say any more about cumulative frequency tables because this book doesn't use them a whole lot. Again, if this were a formal statistics course, there's a lot of applications for that. But okay, so let's get into some of our calculations. Before we can talk about numerical summaries of the data, I mean, graphs and tables are great for summarizing the data and making a quick reference, but if you're talking to somebody over the telephone, it's kind of hard to show them a graph. Now, I realize modern technology, you can send them a picture while you're talking to them on your cell phone, but there are times when you need to be able to communicate it with just a few simple numbers. In order to make sense of describing data with numbers, we need to talk about a distribution. The simplest distribution I can come up with is a dot plot. And what a dot plot is it is just a number line that covers the range of the data. Let's say that on this last test, we had scores ranging from 60 up to 95. That's as far as I can fit on my number line. So now we go through the test. We take a sample of the test that we've given. Let's say the first score is 74. So I'm going to put a dot above the 74. Sample another one, it's an 83. So I put a dot there. The next one is a 77. Next one might be a 91, then an 81, a 79, 68, 75. Another 77, so I put a dot above that one. And I keep looking at the tests and plotting their score on this number line, letting the dots build up if they repeat. And if I plot enough of those scores, this dot plot starts to take a shape. If I were to draw a curve through the top dot in each column, I get a shape like that. And if I plot enough of those dots, it's bell-shaped. You guys have probably all heard of the bell curve or curving scores. That is a bell curve is what they're talking about. The technical name for this is the normal curve, because it is the shape that data normally takes in nature. The height of people would be a bell curve, a normal curve. Lifespan of animals, of each type of animal, would be a bell curve like that. So there are two things we can describe about this bell curve. First is the center of it. This one, I might describe the center of it as being at 79. If I compared that curve to this curve, how would you compare them? That one has a center at 79. This one appears to have a center at 66, right? It has different centers. Well, let's go back to that red curve and compare it to this light brown curve. Those have the same center, don't they? So how would you describe the difference between the curves? The width, exactly. The red curve is wider. The light brown one is narrower. That is referred to as the spread or dispersion. So those are the two things we can describe about these distributions, these bell curves, is the location of their center and how spread out they are. So let's start talking about measures of center. Yep. Now, there are many different ways of measuring the center of a data, or summarizing the center of a data numerically. If our data set is a perfect bell curve, all of them should give you exactly the same number. The problem is our data sets are usually not perfect bell curves. If it is symmetrical, that is a perfect bell curve. All of them would be the same. But because they're usually not symmetrical, I apologize, my handwriting is horrible tonight for some reason. They are what we call skewed, which means they're not perfectly symmetrical. This one is stretched out in which direction? To the left. That would be called skewed left. This one, if I can draw it well, is skewed right, because it's stretched out to the right end, the right side. If the data is skewed, each of these measures of center will be slightly different. If it were symmetrical, if it were perfectly normal, they would all be the same. The way they are different tells us which direction it's skewed. So our measures of center. First of all, I need a set of data. So let me just create a small set of data here that we're going to use. So there's my set of data, 7, 18, 11, 23, 12, and 16. Obviously a pretty small set of numbers. Our first measure of center is the mean. Not talking about the personality of your math teacher. The mean is what most of us have always been taught is the average. We mentioned something earlier called n. What did n represent? The size of the sample. How many items are in it? So what's n for this little sample here? 6. N equals 6. There are 6 numbers in it. That little symbol that looks like a funny E is actually the Greek letter capital sigma. It means sum or add up. X means each number. So the mean is found. You add up the numbers and you divide by n. So you add them up and divide by how many are there. You've used this before, I'm sure. Symbol for the mean, if it's a sample, is X bar. X with that little bar over it means mean. By the way, if it was for a population, it'd be the Greek letter mu is the mean. So let's calculate the mean of this sample. 7 plus 18 is 25, plus 11 is 36, plus 23 is 59, plus 12 is 71, plus 16 is 87. 87 over 6 is 14.5, is that correct? Perfect. That's our mean. Our next measure of center is the median. The median is the middle. Now, all of these are trying to describe the middle, but the median is physically in the middle. To find the mean, it takes a few steps. Step 1, we have to put the numbers in order. So the smallest would be 7, 11, 12, 16, 18, 23. That's step 1. We put them in order from smallest to largest. 2. Find the location of the median, of course. The location is found by doing n times 1/2 or n times 0.5. Well, what is n here? 6. So 6 times 0.5 is 3. Since that is a whole number, it means it is between that and the next location. So what do I mean by that? If I look at my data set, 1, 2, 3, 4, 5, 6, numbering them from smallest to largest, and the next, yes. So looking at this, that came up with a 3, so it's between the third and the fourth number. How do I get between the third and the fourth? Well, I take the third and fourth numbers, I add them together, and I divide by 2. 12 plus 16 is 28. Divided by 2 is 14. The median of that set of numbers is 14. Notice that's pretty close to the mean. The mean was 14.5. That's not bad. By the way, that was step 3. I kind of skipped over that. Step 3 was pick out the mean then from the list, or the median from the list. Now this worked out this way because n was even. What if n were odd? For example, I'm going to give you another set of data here. I'm going to put it in order just to make life easier on us. There's a set where n equals what? 7, yes. So to find that position, it's 7 times 0.5, which is 3.5. Since that is a decimal, we round up. So that means the fourth number in the list is our median. 1, 2, 3, 4, that's the 20. So the 20 would be the median for that list. Our next measure, now, yes, somebody said you cross them off. Yes, you can do that. When you have a small data set like this, yeah, cross off the smallest and largest, smallest and largest, smallest and largest, that's in the middle. If you had 200 numbers, that might take a while. Now, I will never give you more than like 20 numbers or so to do. That'd be the largest data set I would give you. The next measure of center is something called the mode. The mode is the one that occurs most often. The mode is generally only useful for discrete numerical data where there's a limited number of options, or where it's most used, where the mode is used the most, is in categorical data. In categorical data, can I find a mean? Yeah, how do I add up red, blue, green, blue, blue? I can't add those up, can I? There is no mean. In fact, there's no median. In categorical data, the only thing I can do to find a center is find the mode. Which one appears the most often? There's another one out there called the mid-range. The mid-range is found by taking the largest number, which is the maximum, plus the smallest number, called the minimum, adding them together and divide by 2, exactly. So back to our original set of numbers here. The smallest is the 7, largest is 23. So this would be 23 plus 7 divided by 2. 23 plus 7 is 30. Divided by 2 is 15. So 15 is our mid-range. So we've got a 14.5, a 14, and a 15. So they're all really close together. That's telling me that this data isn't perfectly normal, but it's not terrible. So if this data is that perfect bell curve, the highest point of the curve, bless you, the highest point of the curve is the number that occurs the most often. Remember those dots stack up, so the highest point is the most common one. So the mode is always at the highest point of the curve. If this is a perfect bell, if it's symmetrical, the mean is also there, and the median would also be there. Which direction is that skewed? Left. And a data set that's skewed left, well, the median, or sorry, the mode is still the highest point. That's my mode. The median is probably going to move over a little bit. The mean is going to be, depending on how skewed it is, stretched out even further. And of course, it's a mirror image when it's skewed right. The mode is still the highest point. So that's my mode. The median would be moved over a little bit. And my mean would be moved over even further. So for the data I have up here, we had a mean of 14.5, a median of 14. The mean is bigger than the median. That's indicating that chances are this might be slightly skewed to the right. Now there's only 6 points in there, so it's really hard to plot them out and get a picture of the skew. Here's my big question. Which is better? We can probably all agree that the mode isn't a great measure of center. So it comes down to the mean or the median. Let's take a vote. Show of hands. How many like the mean the best for the measure of center? Usually I get a lot of votes on that one because it's the one you've used, you learned in like 3rd or 4th grade, you add them up, you divide, it feels mathematical, right? How many of you show of hands and say the median is better? There's a few hands. How many of you don't care? They are different. Now I said if it's perfectly symmetrical, it's a perfect bell curve, they should be the same. Let me give you an example. Usually most people in the class would select the mean just because one thing is that they've been doing it since middle of elementary school And that adding them up, dividing it out, it feels mathematical. It feels like you're really doing something productive. The median is a little bit unsatisfying. You're just finding that middle and don't feel like you calculated anything. Well, let me give you an example here that might make a point on this. I don't remember now if it was 1982 or 1983, so I'm just going to say 1983 approximately. University of Virginia advertised that the average, that color ain't going to work, average starting salary for a marketing graduate was approximately $78,000 per year. I don't remember the exact number, but it was right around $78,000 a year. Starting salary, by starting salary, it means that's your first job out of college. Yeah, that would be really good money right now. $78,000 a year, I might change careers. Back in 1983, to put this in perspective, your average high school teacher was starting at between $16,000 and $18,000 a year. That was a lot of money in 1983. What they failed to disclose was one of the graduates who did graduate with a marketing degree was a man by the name of Ralph Sampson. Mr. Sampson was 7'4". Two-time NCAA Basketball Player of the Year. Number 1 draft choice, the Houston Rockets in the NBA. Anybody want to guess how much Mr. Sampson made that year? Millions, right? Even in 1983, the top draft choice in the NBA made $5-10 million. Do you know how many $20,000 a year marketing graduates it takes to average a multi-million-dollar contract to $78,000? A lot. Mr. Sampson was the only one in that graduating class with that degree that made more than $33,000 that year. If you took his salary out, the mean, obviously that was the mean with the salary in there. If you took his salary out, the mean was, I can't remember exactly, it was like around 24,000, 23 or 24,000. Even with his salary in there, the median was about, I can't remember exact numbers, around $26,000. Without it in there, the median was around 23. Now notice, including his salary, took the mean from 24 up to 78. It only took the median from 23 up to 26. It's what we call stability. The median is more stable. The opposite of stability is sensitivity. The mean is more sensitive. One really large value or one really small value can radically change the mean, but it doesn't change the median by as much. I just love that example because there's an example of statistics used completely honestly. There is not a single lie in that statistics. Is it, really ethical though? Is it a true picture? No. And that comes back to that point of statistics can be twisted and Samuel Clemens, I don't know if you know who that, otherwise known as Mark Twain. We just had a flash. Did you guys lose my computer screen? We're good? Okay. Mark Twain once made the comment of, there are lies, there are damn lies, and then there are statistics. And there's very much so. Somebody that knows what they're doing. There are fields out there that pay a lot of money to people that are good with statistics to use those statistics to tell them what they want to know, and then to use those statistics to tell other people what they want them to hear. That's one place they're used. There's a whole field out there called actuaries. Actuaries use statistics they'll use statistics to set rates for your insurance premiums. They use statistics to help companies decide whether starting a new company or starting a new product line is worth their money or not, whether an investment is worth it or not. So, yes, it's a big field. Marketing is actually a very small set of statistics. They are used they're a huge tool in marketing, but it's a very small set of where they're used. A lot of statistics behind the scenes in companies, and marketing is one of the places where they come to the surface. I talked a lot about that deception and stuff like that in statistics. We talked about the samples and gathering the data. There's so much that can be done there at that level of gathering data. The way I choose the sample. Some things that are done, I'm getting a little off topic. We'll come back to measures of center in a little bit. But, we talk about the random sample. For a short period of time, I actually worked for the UW-Madison Statistical Research Center, and they were hired by companies to do statistical surveys. Work-study students worked there, and they had what it was a computer screen in front of them. The computer actually dialed the phone. They didn't actually have a telephone. Computer dialed the phone, and then the script came up in front of them. Good morning, and it put the name of whoever they're talking to there, or good afternoon, or whatever. Mr. Johnson, I am calling from the University of Wisconsin-Madison Statistical Research Center. Today, I'd like to ask your permission to do a survey on, and give them the topic. Or a lot of times they didn't even give them the topic because telling them the topic could jade them. If I said, I'm going to give you a topic on welfare, and you're somebody who's adamantly against welfare, you're going to say, no, I don't want to talk about that. I'm out of here. One of the studies we got, and it's long enough ago I can say it, was by Bill Clinton's administration. Wanted to do a survey on the whole scandal that was involved there, as to whether the public thought it mattered or if they wanted them to just drop it. And what they did there was a stacked survey. The first 5 questions or so that were asked were totally meaningless. It was to feel out who they were talking to. Now, the person on the phone had no idea this was happening. All they did was read what came up on the computer screen. It brought up a question, they entered an answer somehow. And so it would ask something like, did you vote Democrat or Republican in the last election? Did you support Bill, or do you think Bill Clinton has done a good job with the economy? Do you think Bill Clinton has done a good job creating jobs and stuff like that? With the budget and all those things. And at the end of those 5 or 6 questions, the computer determined whether this person thought what we wanted them to think or not. So then at the end of the 5 or 6 questions, either it would pop up on the computer screen and the person on the phone would say, well, thank you for your time, Mr. Johnson. We appreciate you answering our questions. Have a great evening. Or it would say, okay, Mr. Johnson, just a few more questions. And if they answered the first ones the way they wanted them to, then they would ask, well, do you think that this scandal is worth our time, or would you rather we moved on and got on to, things like that? So that they had a pretty good idea how they were going to answer the questions before they actually asked them. Now, yes, it was the Monica Lewinsky deal. Yeah, I was going to say grass hut for the 90s, or so. The other thing that would be done is wording. Emotional words were the big thing. Now, if I called you up and said, okay, I'm going to ask you a survey, and I start out, would you be in favor of raising taxes? Now, at that point, do you hear anything else I say? No. But would you be in favor of raising taxes to pay for better school lunches in our schools? Well, all you heard first was raising taxes. You've probably made up your mind. If I worded that as, if it meant our children could have better lunches in their schools, would you be in favor of paying a few dollars more a year in taxes? More likely to get more yeses for that one. So that wording, using those emotional words, using the children is always a big one. Yes. It is almost 7:20, so we're going to take our second break here. It's 7:19. Let's come back at 7:29. So we need to talk about measures of spread. Measures of spread or dispersion is the other word that is sometimes used for them. How the data is dispersed. Now I need a small set of numbers here, so I'm going to make up another set here. Seven, 12, 13, 14, 19. I'm going to put them in order from smallest to largest, just to make it simple on us. One of our first measures of spread, the simplest one, is the range. Now, the last measure of center we talked about was the mid-range. The range itself is very closely related to it. The mid-range, we took the largest, added the smallest, and divided by 2. The range, we take the largest, and we subtract the smallest. That's it. So the largest here is 19. We're going to subtract 7, gives us a range of 12. The range is not very precise. If this were a technical math class, we would talk about precision. Precision is defined as the ability to distinguish between two similar things. For example, let's say I put this data set up here. What's the range of that data set? 19 minus 7 is 12, yes. They both have a range of 12. Would you say they're the same amount spread out? No. If we did a dot plot here, let's do 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This top one has a 7, 12, 13, 14, and 19. The bottom one has a 7, 8, 13, 18, and 19. Well, the bottom one, the purple one, is obviously more spread out. But the range does not distinguish between them. It is not very precise. So we use the variance and standard deviation. So those are two numbers. The variance is going to be one and the standard deviation is the other. I list them together because they're all part of the same process. You get the variance, and then one more step, you have the standard deviation. I'm not even going to write the formula up here for this because the formula itself is quite confusing. To get the variance, it is a 5-step process. The standard deviation adds a 6th step to it. The standard deviation is really the important number here. It's the one that gets used the most. So let's go about talking about the standard deviation. It is 6 steps. Step 1, is to find the mean. So let's do the top data set up here. 7 plus 12 plus 13 plus 14 plus 19. If we add those up, we get 65, right? Divided by 5 is 13. So the mean is 13. That's step 1. Step 2. To subtract the mean from each number. What do I mean by that? Well, our numbers are 7, 12, 13, 14, and 19. We are going to subtract the 13 from each. What is 7 minus 13? Negative 6. 12 minus 13? Negative 1. I'll let you do 13 minus 13. 0. There we go. 14 minus 13 is 1. 19 minus 13 is 6. These numbers right here, by the way, that we just calculated, are called the deviations. That's how far each number is from the mean. Now, I quickly made this data set. They're not always going to be symmetrical like that. However, if I did add them up here, the deviation should always add up to 0. You don't have to do that because that's not really part of the calculation. But if you wanted to double check yourself at this point, if they didn't add up to 0, usually that means you probably had something wrong in your mean when you calculated the mean. Step 3 is to square each deviation. So negative 6 squared. Now be careful. I want you to punch this in your calculator. Should be positive 36. How many of you came up with negative 36? Anybody? Okay, y'all remember to put the parentheses around it when you did the negative 6 squared? If you're not careful, if you just do negative 6 squared, your calculator may try to tell you that it's negative 36. You have to put parentheses around it when you do that. When you square a negative, there has to be parentheses. Any number squared should be positive. So don't let your calculator tell you it's negative. Negative 1 squared, 1. 0 squared is 0. 1 squared, 1. And 6 squared, 36. Those, by the way, are called the squared deviations. Next, step 4 is to find the sum or the total. If we add those up, what do we get? 74. That is called the sum of the squared deviations. Yes. Yes. Sure. Yep. All right. Okay. Your calculator is going to look a little different than mine, but the keys will be the same. You have to do the open parentheses. Now the key is the negative. Don't push the minus key. Down by your equals key, there'll be a negative key that looks like that. It's a negative in parentheses. You got to use that. Then the 6. Then close parentheses. And then you should have an x squared key somewhere. Then hit enter and it should pop up 36. You bet. Next, step 5. Step 4 was adding them up. Step 5 is to divide by n minus 1. For this data set, what does n equal? 5, because there's 5 numbers. So n minus 1 equals 4. Yep, so we're going to divide by 4. So that ends up being, what, 18.5? Is that right? That magic little number we found right there. By 4, yes. So that result we get there after we divide by n minus 1, that is the variance. It's a simple 5-step process to the variance. Notice the grin. Might have been a little sarcasm there. Oh, sure. Yeah, step 3 is just squaring each of them. And then step 4 was just to add them all up. This is not something I want to do by hand very often. That's why I would never give you more than like 5, 6, 7 numbers to do a standard deviation. You can tell if I'm mad at you if I give you like 12 numbers and tell you to calculate the standard deviation. You never anger a math teacher. They can always hurt you. So yes, then step 4 is to add up those squares. Then step 5 was to divide by n minus 1. Remember, n is the number of items in the list. So there's 5 items in the data set. So n minus 1 would be 5 minus 1 equals 4. So that's why we divided by 4 there. Dividing by 4 gives us 18.5. That's the variance. Now there's one more step to find the standard deviation. The standard deviation, we have to do the square root of the variance. To do the square root, most of your calculators, it's a second function or a shift. So either hit second or shift. Then above your x squared key, there's a square root symbol. Type in the 18.5 and hit equals. So 4.301. Come on now. I'm going to round at 4.30. Now, I always get the question, how do we know how to round to 4.30? Why didn't you go 4.301 or just 4.3? Well, rounding rule of thumb. Now, like any rule of thumb, this only applies if you're not told what to do. Most problems will say round to the nearest tenth or the nearest hundredth or whatever. But if it doesn't say in the problem where to round, for measures of center, That'd be like the mean and the median. You round to 1 digit beyond the data. What does that mean? Well, our data here was all whole numbers. Since that's all whole numbers, the data goes to the nearest 1, right? So that means measures of center would be rounded to the nearest 10th. That's 1 place value past the data. Spread is 2 digits beyond the data. Variance and standard deviation are spread. So since the data went to the nearest 1, this is going to go to the nearest 100th. So the data only went to the whole number. The means and medians would go to 1 decimal place. The spread, the variance and standard deviation would go to 2 decimal places, or the nearest 100th. Let's prove that this is a precise measure. So that data set we had gave us a standard deviation of 4.3. We had another set of data that was 7, 8, 13, 18, and 19, right? What's our first step? Find the mean, right? I'll race you. I made the data set purposely so I had the same mean. What's step 2? Subtract the mean from each. So I got 7, 8, 13, 18, and 19, and I am going to subtract 13 from each of them. Do that quick in your notes. It's going to be symmetrical again. You are correct. Come on now. Stay there. Wow. So 7 minus 13 is negative 6. 8 minus 13 is negative 5. 13 minus 13 is 0. 18 minus 13 is positive 5. 19 minus 13 is positive 6. What is step 3? Square them. Square each deviation. Negative 6 squared is 36. Negative 5 is squared is 25. 0 squared, 0. 5 squared, 25. And 6 squared is 36. Step 4. Add them up. Find the sum. 122 is correct. We're going to wait a little second. I'm guessing people need a second to catch up with me. Okay, so what's step 4 or step 5? We're going to divide by what? By n minus 1. N is 5. So we're going to divide by 4, which gives us 30.5. What's that called? Variance. What do we do with that? We square root 30.5, gives us 5.52. That is the standard deviation. Yes. Yep. So for the square root of 30, most of your calculators, the square root is a second function, and it's above the x squared key like that. So I cleared out. So to access that, you either have to hit second or shift, then that x squared key, which should have the square root above it, and then type in your number, 30.5, and then hit enter. Did it work? I'm sensing a serious lack of boundaries in this group. Did you guys get the calculator to work? Okay, perfect. Now, the last thing I want to show you tonight, that sounds way more promising than it is. What if we're given a frequency table? And this is going to be a discrete numerical data. This can only be done with numerical data. It's much easier with discrete. It can be done with continuous data. I'm not going to do that to you. In fact, the discrete data would be an extra credit question on a test. But I'm going to show it to you. Just because my creativity is gone, we're going to call it the value. Let's say I have values of 1, 2, 3, 4, and 5. You know what? Let's do 1, 2, 3, and 4 so that I don't have to work so hard. And the frequencies of 3, 9, 6, and 2. First thing we're going to do is we're going to find the mean. We're going to call that process A. Step 1 to finding the mean. Multiply the value times the frequency. Why are we doing this? Well, because what this is saying, the value is 1. How many 1s are in that set? There's 3 of them. So this data set is literally 1, 1, 1. How many 2s are in the set? There's 9 of them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then there's 6 3s and so on. Well, the thing to find the mean, we have to add them up, don't we? So by multiplying the value times the frequency, we're just starting to add them up. So there's 3 1s. So 1 times 3 is 3. The 1s total up to 3. There's 9 2s. 2 times 9 is 18. So the 2s would add up to 18. How many 3s are there? Yeah, 3 times 6 would be 18. The 3s add up to 18. And there are 2 4s, so 4 times 2 is 8. So again, that would be just like writing out all these values and adding them up, but we still have to add up this column, step 2, find the sum. That adds up to what? 47 works to me. Then step 3, divide by total frequency. The total frequency here, if I add those up, is 20, right? So my mean is 47 divided by 20, or 2.35. That's my mean. I'm cheating. That worked out well. So I'm just kind of reconstructing my table in Excel here. What were my frequencies? 3, 3962. Okay. So value times frequency. Yeah, I'm going to make Excel do this. There. I've got to find the total frequency and the total of this column so I can sum them. Those are my totals. So then my mean is just equal to that divided by that, 2.35. The reason I did that was because the next thing we're going to try to find is the standard deviation. Standard deviation requires a little more work. Now, if you look back, remember our steps to standard deviation. We just found the mean. After you found the mean, what did you do? There you go. We subtracted the mean from each number. Value minus the mean. So here that's going to be this number minus, what's our mean? 2.35. Oops, I screwed that up. Yep. So 1 minus 2.35 is negative 1.35. 2 minus 2.35 is going to be a negative 0.35. Darn you. There. Then 3 minus 0.35 is going to be 0.65. And 4 minus 2.35 is 1.65. So those are differences. I'm going to pause there, let you guys catch up. So I just subtracted my mean of 2.35 from each of those original values. In our regular standard deviation, after we subtracted, what was our next step? Square them. So negative 1.35 squared is 1.8225. Negative 0.35 squared is 0.1225. 0.65 squared is 0.4225. 1.65 squared is, I'm going to pause for you guys to copy those down, don't worry. Now, after we squared them, what was our next step? Add them up. Now, this is where we've got to adjust it a little bit. For the mean, we didn't just add up these values, did we? What did we have to do to them? We had to multiply them by the frequency. This number here, this squared deviation, the 1.8225, does not happen once, it happens 3 times. So I'm going to take the square times the frequency. So 1.8225 times 3 gives me 5.4675. Then I have to do the 0.1225 times that frequency of 9. That's 1.1025. I take the square of the 0.4225 times its frequency is 6. Gives me 2.535. I take the 2.7225 times its frequency of 2, 5.445. That's what I have to add up. I add them up to get 14.55. What's my next step? What's n here? Total frequency is 20. So I'm going to divide by 19. That is the variance, 0.765789. Calculate the standard deviation from that. What do we have to do? Square root. Square root of 0.765789 is 0.875094. So 0.88 would be my square root, or my standard deviation. On a test, this would be an extra credit question. Both the mean and the standard deviation of a frequency table like this would be extra credit. They will be on the test. I'm going to tell you that right now. They will be extra credit. So it's a great way to get yourself an extra, 10 or 12 points on the test if you can do it. And it's not, the mean especially is not that hard. And really, if you compare this to the process of calculating the regular standard deviation, it's not that much harder than a regular standard deviation. Yeah, just you have to multiply by the frequency of that rate step. Any questions? Well, it would be in different parts. You have to find the mean, standard deviation. So, I would separate the mean and the standard deviation. Okay, I get the feeling you guys have had enough for the night. New homework due next Wednesday. No quiz this week because there was no homework last week, so there is no quiz to worry about until the 5th, I think would be our next quiz, right? Just have a good week. There will be a quiz next Wednesday. There's no quiz tomorrow. No quiz tomorrow.